Okay. All right, I think it's about time. So today, I want to talk to you guys a little bit about how we integrate using alternative coordinate systems. So we're going to do polar today, which is a sort of warm up to more general change of coordinates. But we'll see that, I don't know, that there's some nice applications already to just knowing how to do integrals with polar coordinates. So what I want to start with today is just a basic fact about how we calculate the area of a trapezoid, which I'm sure you all know. So if I take, let's see if I can draw a trapezoid here. Let's say I take trapezoid and two sort of heights, or two lengths on top, and call them B1 and B2. I have a height, call H. And if I want to calculate the area of this guy, then the area is just equal to, essentially what you do is you take the average of these, the length on the top and the length on the bottom, and then you treat it like a rectangle. And you can sort of do some solid geometry to just kind of rotate things around and see that's indeed what you should expect. So this is like height times the average of the lengths of the base and at the top and the bottom. So times 1/2 B1 plus B2. So we want to use this to kind of get a good estimate of something called a polar rectangle. Okay, so let's talk about polar rectangles. Let's talk about their area. So what is a polar rectangle? Well, a rectangle is the way we describe it in Cartesian coordinates, at least when we're doing integrals. Maybe you want to think of this as a sort of horizontal or vertical rectangle. So in Cartesian coordinates, we describe this by these two sort of sets of inequalities. We bound both coordinates by some constants. And so that's our rectangle in Cartesian coordinates. So what is it in polar? It's the same idea. We just want to bound the two polar coordinates we have. We'll bound r by a and b, and we'll bound theta by alpha and beta. So the notion of a polar rectangle, I'll call this r. So what does it look like? Well, it depends on what our values are, but one way, sort of a general perspective you could have is you can say, all right, well, let's bound theta first. Let's say this is our lower bound for theta. I need a little more room. And then we take the same guy, duplicate it. And we'll just kind of rotate it so that it's now theta's worth away. And so now we just need to specify it. The r bounds, let's say we have this upper r bound is a, or sorry, it's b, pardon me. So we have b here, and then a lower bound would be a here. So what are we left with if our radius is bound between A and B is going to be this region in here. So it's it's sort of a part of a wedge, if you want, an angle sector. So what I want to do here is I want to estimate the area of these polar rectangles, which will be a good estimate when these are very small polar rectangles. So let me okay, so what's a good estimate of the area here? So let me say what I mean here. So instead of using alpha and beta, since these are going to be sort of my global bounds, let me use theta. Well, let me call this. Let me do this one. I'll say let's let delta theta this be equal to beta minus alpha for this global one, and let delta r equal b minus a, just for this case. Okay, so it's going to be the change in our r and the change in our well, what I want to do is I want to sort of take this picture I have of this sector, and I want to sort of rotate it and see this as sort of a trapezoid is my point. Consider this as a trapezoid. So view as a trapezoid. And then what I have is I can certainly estimate what up here are B1 and B2, because there's a simple formula for sort of this length, right? This length here is really just going to be this delta of theta times B. And this length here is going to be delta theta times A. Sort of how radians work in a sense. So here we have delta of theta B. Here we have delta of theta A. And our height, well, if we imagine this as being very small, we can sort of estimate our height as being this length here, which is just going to be this delta r. So the estimate here of this, it is an estimate, it's going to be delta r times 1/2 delta theta times A plus delta theta times B, or delta r times 1/2. Well, let me actually kind of move things around. 1/2 A plus B times delta r times delta theta. Okay, this is the formula I wanted. All right. Now, I'm going to use this formula now to talk about how we can form the integral of a function over a polar rectangle. So now let's do that. Double integrals over polar rectangles. Okay, so let me just draw a couple of circles here. And what I want to do is I want to imagine that I have this polar rectangle. So I have some kind of sector here. And I want to integrate over this polar rectangle. So this polar rectangle is right in here, and I want to integrate a function that is defined on that. So I'll have some function f r theta defined on r. distances are. So what I do is I do what I want to integrate this function. So I want this integral, but I don't want to go to Cartesian coordinates. I want to stay in my polar coordinates. So what I need to do is I need to do what I did in Cartesian coordinates. I need to break up my region R into little regions, estimate the area of those little regions, choose sample points, multiply the area of those little regions by the value of the function at those sample points, and then take limits. Add everything up and take limits. So to do that, we do what we did. So we break up our region. So we need to break up, we want to form a double Riemann sum, partition the region into smaller polar rectangles. So what do? We choose partition A equaling R naught, R1, just say R sub M equaling B. And we'll take theta naught to theta n equaling beta. And we're going to write down this double Riemann sum. Take the sum of I equaling 1 to m, sum of j equaling 1 to n of f. And remember, we do need to choose sample points. So I'll write this R sub I star, theta sub j star. And then I have this delta area, Aij. And this is why we did what we did in the beginning, is that we have an estimate for this small area once we have a small polar rectangle. So we can use this estimate here. Oops, here. And write it down. Now here, A and B are Ri and Ri minus 1 and Ri. And delta R and delta theta are the differences of the thetas and the R's and the thetas. So this is going to equal, well, it's the same thing here. And now we just need to put in our formula. So we have 1/2 Ri star, oops, not Ri star, Ri plus Ri minus 1. Well, I already have that. Let me put the 2 down here. Times delta R, delta theta. And you can write delta Ri if you want. That's fine. So, however you want to do it. So now here's the trick. So this is a double Riemann sum, which is really kind of impossible to understand in general. But what you can do, assuming that you know that the integral exists, which you do because let's assume f is integrable, you can make a very judicious choice of your sample points. What you'll notice about this number is that it is the averages of the R's. So what we have is we have this partition here. Let's think about what we're doing here. We have a partition of our R's, right? We start at R naught, that's the first length. Then we go to R1, R2, and keep on going, right? Up to Rn. We've also divided up our thetas to these regions. But now the point is that this value here, that's the average, that's the midpoint between Ri minus 1 and Ri. So that point is actually a point that sits right in between these two guys. So we can choose our sample point so that its R coordinate is precisely that number. So I'm just saying we choose something, choose our sample points. The theta is not, it can vary, but let's choose our R coordinate of our sample points to be the average. So we'll write that down. then we get the following formula. And this Riemann sum, I'll just copy the thing. Looks like this. Ri star. Now that is good news because this is an ordinary looking Riemann sum. In other words, we're petitioning an ordinary rectangle in polar coordinates. It's a polar rectangle when we look at it in Cartesian space, but in polar coordinates, this looks like an ordinary rectangle and an ordinary Riemann sum, not of the function f, but of the function f times r. So what that tells us is that this double integral of r, if we take limits of f of r theta dA, is equal to the ordinary integral, iterated integral by Fubini from a to b alpha to beta of f of r theta r dr d theta. We pick up this factor right here. So that's why, I mean, at this level, that's why we see this R. We'll see that there's a general way you can obtain this factor of R from an arbitrary change of coordinates theorem, from a change of coordinates theorem that allows for arbitrary changes of coordinates. But for polar coordinates, this is the main formula that we want to be able to use. Okay. Let's do some problems. Let's do some problems. Enough theory. All right, so let's find the volume of a ball of radius r. I know you guys all know this, but okay, let's do it anyway. Well, let's set up the integral. So we have a ball, it's radius r. So one thing I can do is I can look at this as being bound, a region that's bounded by two functions, or even just one. If I want, I can say that the volume of this ball is equal to twice the volume of the upper half ball. I just break that volume of this guy. So let's look at the volume of this guy first. So the upper half ball is a region trapped between a function and the xy plane. Okay, and so this is equal to 2 times the double integral over this disk of radius r, call it d sub r, of the function, which is it's essentially the function for the sphere, but let's see, it's r squared minus x squared. So where do I get this function? This function is because we know that the equation for the sphere is just this. And so if we subtract x squared plus y squared from both sides and take square roots, we'll get the upper hemisphere. So we've written down our volume in terms of a double integral. dr here is just the disk So it's the set of points x, y, so that x squared plus y squared is less than or equal to r squared. All right, so this is the integral in Cartesian coordinates. You could write dx dy here. You could see that the disk is indeed both a type 1 and a type 2 region. You could find, the bounds for that, and you could do a double integral, but it's not a very pleasant or fun double integral, right? So in some ways, I don't advise you using Cartesian coordinates for a problem like this. And as a rule of thumb, if you're looking at a problem and you see a lot of x squared plus y squareds, right? Consider switching to polar coordinates. It should be something that comes to mind. Not necessarily the best option, but oftentimes it is. So now we want to switch this to polar coordinates, which means we have to write the integrand in terms of polar coordinates, and we have to make this switch where dA doesn't go to dr d theta, but goes to r dr d theta. So let's do that. I'll just write it down here. So I need that factor of 2 that I'm going to keep in mind. And I'm going to now integrate, well, my polar rectangle. We got r squared minus lowercase r squared, that's x squared plus y squared, times r dr. And what are my bounds for r? Well, the disk this is a polar rectangle. R is allowed to vary between the radius and 0, and theta is allowed to be anything it wants within the polar coordinates world. So theta is allowed to vary from 0 to 2 pi. So when I put those bounds in, go 0 to r, 0 to 2. All right. And now it's just a matter of computation. So let's do that. I'll keep this integral out. I'm going to, now you'll notice that you've actually received a lot of help just by changing coordinates. And this is a feature of this. This extra r really helps because now you're able to make a substitution and life is grand. So here you're going to get a 1/3 times r squared to the 3/2. And I think I need a negative here. R d theta. So at r, this is 0. And at 0, this is 1/3 r squared, capital R squared. So since we're subtracting that, we'll just get 2 times square root 0 to 2 pi of r squared over 3. But of course, capital R is a constant, it's the radius of our ball. So we can pull that out. We get 2/3 r squared. I'm sorry, I think I messed up here. R cubed. I forgot to take the square root. Okay. There we go. Cubed times this integral. But of course, this is the integral of 1 from 2 pi to 0. So that will give you 2 pi. So we get 4 pi r cubed over 3, which is familiar. Okay. Questions? This here? Yeah. So it's easy to overlook it because I'm just blocked it out. This is important, right? Right. So I'm just using a u substitution for r squared, but I'm just saying that I'm using a power rule here. So I know that r squared minus r squared to the 3/2. What's the derivative of that? Well, what's the derivative of that? The derivative of this with respect to r is going to be negative 2r times 3/2 times r squared minus r squared to the 1/2. So I get precisely what I have here, except I've got a negative 3. So I just multiplied that by negative 1/3. And I'm in business. Is that okay? I don't want to have to write du and all that too. Is it okay to do that? You guys can do it. Yeah. Yeah. This is just so maybe it's easier if you write the r. So maybe it's easier to write the r over here. I don't know. It's just a u substitution. If you want, you can take u to be r squared and go ahead and do that. Okay. Or u equal to r squared minus capital R squared minus r squared, either one. Okay. So I'm sorry, I'm a little low energy today. I'm kind of, but it's really so I do want to say something kind of like general, but I'll leave it mostly to the problems. So you can also do polar coordinates over more general regions. So you could have kind of a region, let's say, that looks like this. And you had some function, you had a couple of functions where the radius is a function of the angle. So h2, the radius is the function, h1, the angle. So, and you're integrating over this region. So then if you wanted to integrate a function f r theta over that kind of a region, this is sort of like a, I don't know, type 1 or type 2 in polar coordinates. Let's say this region's R. Then this is just going to be, I mean, again, you'll have some, you just bound your radius now with these functions. So there are a couple of problems in the exercises like this. Let's say this is alpha and this is beta. So you do get this kind of a, you can, all I'm saying is you can do this kind of integration over more general regions than polar rectangles. And sometimes, again, that's helpful if when you look at your function, well, first of all, when you look at your domain that you're integrating over, that it has this kind of structure, but also your function should simplify a little bit when you put it into polar coordinates. Otherwise, this is not a very helpful thing. All right. Let's do another, we'll do another general kind of problem, maybe just to get a little more of the hang of it. Okay, so let's let, I don't know, we'll call it E, be the region. Trying to make this a little more interesting. Let's say y is less than or equal to 0. I don't want y. I'll say y is greater than or equal to 0. And then x squared plus y squared is less than or equal to z squared is less than or equal to y. So now find the volume of E. So for me, again, like it's helpful to kind of draw a picture first. Although I don't know if it's strictly necessary here, but I think it's helpful. So this, again, so where is y positive? Y is positive on this side in this half plane, right? So we can consider this half space everything above and below this shaded region. Oops. Now, what is this? What are these bounds? Well, z squared less than or equal to 1 are just, if you want z less than or equal to 1, gives us sort of a height bound. So we can take z equaling 1, and we know that everything is below that number. The most interesting bound, of course, is this bound here. And if you look at that bound, this is this equation, x squared plus y squared minus c squared equals 0, which we've actually seen before. This is a quadric, and it's a cone. And so what we have, or if you want, you could also see that this is x squared plus y squared is equal to z, square root of x plus y, or r is equal to z. So what you'll get is you get this kind of cone. This. I don't know if that's clear. It's a circular, imagine a cone and just slicing it in half. Is it? Maybe I can clean it up a little. Let me try to clean it up. Okay, so we want to find the volume of this. Well, we can drop this cone down to the xy plane, and we'll get this half disk. Get the half disk. So in the xy plane, so E is bounded by functions 1 and x squared plus y squared over the region x squared plus y squared less than or equal to 1, and y is greater than or equal to 0. So this is half of the unit circle. If I draw the xy plane, I get this half disk. So if I want the volume of E, well, I could take the volume under the constant function 1 and subtract the volume under the function x squared plus y squared. So this is going to equal, let's call this region R. It's going to equal the integral, double integral over R of 1 minus x squared quantity x squared plus y squared dA. And again, you see in the integral, an integrand, you see this x squared plus y squared. You also look at your domain, and that domain is a polar rectangle. What are the bounds for R and theta for this polar rectangle? For R, any ideas? Yeah, less than or equal to 1, right? And we put in greater than, R has to be non-negative, but okay, we'll put that in there. And for theta, it's going to, yeah, between 0 and pi, great. Good. So once we have that, we can convert this to an iterated integral using our formula for polar coordinates. The bounds for R, 0 to 1, bounds for theta, 0 to pi, 1 minus R squared And then we, instead of putting dr d theta, we put r dr d theta. Okay, so let's just go ahead and integrate. So here we have r minus r cubed. So it's going to be r squared over 2 minus r to the 4th over 4 from 1 to 0 d theta. And well, at 0, that whole thing is 0. At 1, we get 1/2 minus 1/4, so we get 1/2. So this is 1/2 the integral from 0 to pi d theta. Sorry, 1/2 minus 1/4 is 1/4. Can't add today. And that is, of course, then just going to be pi over 4. All right. Good. All right, so now I want to show you something magical. It's an amazing, really amazing thing. And something very useful. And something you can't do really. So some of these problems you might say, well, I learned how to do shells or whatever you did in one variable calculus. I can compute volumes using just ordinary integrals. That's true. So some of this stuff is much more useful if you're not calculating volumes, but you're calculating, actual integrals of functions that aren't constant. But okay. Here's an application that's really just not something you will see in a one variable, or would be able to do in a one variable calculus. So it has something to do with density functions and probability theory. So a density function will be some function rho from R to 0, 1. And what you want is this to kind of reflect the probability of something landing in a certain interval. And for that to make sense, you want to say that you want to normalize it. You want that rho of x dx is equal to 1. You want the probability of something happening to be 100%. You don't know what it is, but something's going to happen. And then, you have this notion of probability of your whatever is going to occur. The probability that it will be between a and b is going to equal this integral from a to b of rho of x dx. Okay. So of course, any kind of system that has any sort of randomness, you want some notions like this. Now there is a very famous function that looks very strange. But maybe you could imagine a very reasonable function, a reasonable thing to consider. So this is called the Gaussian distribution. You guys know it. You guys know about Gauss? Yeah. Oh, don't groan. I mean, come on. Gauss is a great, great guy. What a sweetie. He was the best. Gauss is the best. Uber Gauss. Yeah. Anyway, other things, what is this also known as? Also like normal distribution. You know about that? Bell curve. All of these are like the same thing. So there's this function, a very wonderful function, e to the minus x squared over 2. What a great function. Who would ever argue with such a beautiful function? It has exponential superdecay, right? As x gets big or x gets really negative. This is going to rapidly, it's e to the negative of x squared. So it's going to rapidly go to 0. And then at 0, it's 1, right? At 0, it's 1. This kind of, this function, or a sort of normalization of it, is everywhere in the universe. It is everywhere. It is ridiculous. It's an extremely important function, and it has wonderful, wonderful properties. Now, if we wanted this to be, this looks like a probability distribution. I mean, it's bounded, it kind of rapidly decays. And so a natural question, if you have something that looks like a probability distribution, you want it often to satisfy this. So sometimes it doesn't, you can normalize it. You just divide by the integral. So let's see, can we do this? Can you do it? Nobody knows. It's a one variable problem, right? What is it equal to? This, you can go see your friends down the hall in your dorm or wherever you are, and you can say, hey, you're in calculus 1. How do you get this integral? And then don't laugh like that afterwards. They'll, you know, well, first of all, I'm sure you don't ask your friends calculus problems very often, but if you do, there would be a really cruel thing to ask a one. There is like, so I've been alive a while. I've never seen an answer. I've never seen any technique that doesn't involve many variables. Even like complex analysis has techniques to do things that I've never seen another approach than the one that I'm about to show you to evaluate this. So it's like an impossible thing to do. Even though it's a one variable problem, calculating this is impossible. However, we sophisticated folk can solve this problem. So what we do is kind of funny. Let's call this A, area. What we do is let's calculate A squared. A squared is this squared. Which is this times itself. Now, when I just think about this, does it matter that I call it X? Can I call it like smiley face or something? I mean, do I need to, I don't care what symbol I use, right? It's going to be integrated, whatever it is. So let's use Y. Now, this double integral I can write as an iterated integral. I'm just doing integral each time. So if I write it as, I mean, since there's no Y dependence here and there's no X dependence here, I can do this as an iterated integral. Now, Fubini tells me, and there is a Fubini theorem for unbounded regions so long as everything is integrable, as it is here. Fubini tells me that this is also the integral, the double integral over R squared, the entire plane. And here I can just use my power law, X squared plus Y squared. Now, have we gained anything? Well, at first glance, not really. See, the problem your roommate or your hallmate or whatever you call those people will have when they try to solve this is they'll try to do substitution, but there's a square here. And they will spend an evening or two thinking about it, and they will start praying for an X to appear here. Because if an X appeared here, like a miracle, then they could use substitution and everything would be great. Life would be fantastic. But they will not be able to make that appear legitimately. But somehow, amazingly, polar coordinates does the job. So I need to go to infinity. So my radius is now I've got the polar rectangle, which is the entire plane. My radius goes from 0 to infinite radius. X squared plus y squared is r squared over 2. Dx dy, r dr d theta. Holy cow. Now I can do great things. I know how to integrate this, right? This is like e to the negative r squared. I guess I get a negative here, over 2. From infinity to 0. Now, as r approaches infinity, this e to the negative r squared approaches 0. So at infinity, we get 0, and we subtract off e to the 0, negative e to the 0. So we're adding, we just get 1. Then we can do this integral pretty easily, 2 pi. So a squared is 2 pi, or a is the square root of 2 pi. I don't know why. That is like the most ridiculous answer though. I mean, you don't find square roots. I mean, look at this function. Would you guess square root of 2 pi for the integral? I don't know. I think most people would not. So this is a very, very nice use of multivariable integration. And well, I'm glad I got a chance to share it with you. I think we'll finish a couple minutes early today, but I will see you Wednesday, or yes, Thursday.